Yo, what's up everyone? Welcome to Descriptive / Laboratory Chemistry. Today we're going to be talking about acids, bases, and pH. Acids and bases are going to have different definitions based on what model you use. And there are going to be three major types of models, and they're not all the same. The first model is one of the most common ones, and it's one of the most simple ones. It's the Arrhenius model. In the Arrhenius model, acids produce H+ ions in aqueous solutions, and bases produce OH- ions in aqueous solutions. So if you look at a general form for an acid, you would have the acid HA dissociating into H+ ions and A- ions. Now, there's an equilibrium symbol here. What this equilibrium symbol represents is that you have a forward reaction and a reverse reaction. So the forward reaction is the acid turning into H+ and A- ions. But you also have the reverse reaction, where those H+ and A- ions that get produced are turned back into your acid. And so when you're at equilibrium, the rates of the forward reaction and the reverse reaction equal each other out. And depending on how dominant the forward reaction or the reverse reaction is, you have different strengths of an acid. Now, although I said that the general form is HA, the acid turning into H+ and A- ions, that's not really the full equation. The full equation is the acid reacting with the water to produce hydronium ions and A-. The hydronium ion is this here, but this way of writing it is really long and it's a lot more complicated than the first one. So generally, we use the first one. We use this one more often, but remember, when we're talking about H+, we're really talking about hydronium ions. And when we're talking about the acid dissociating, it's dissociating when it's being reacted with water. Alright, let's look at some examples. So one of the first ones you have is perchloric acid. Perchloric acid is dissociating into H+ and chlorate ions. The full reaction is that the perchloric acid is reacting with the water to produce hydronium and the chlorate ion. But again, we use the top one because it's a bit more simpler. Another example is phosphoric acid being dissociated and also carbonic acid being dissociated. Now you may notice a difference between the first one and the bottom two. The first one uses a forward reaction and the second one uses an equilibrium, and the third one. Why this happens, we will talk about a bit later when we talk about the strengths of these acids. But for now, just know that all of them are equilibrium, except when you have a strong acid or a strong base, it's easier to just say it's a forward reaction. And again, we'll talk more about this in a little bit. Okay, let's talk about the general form of a base under the Arrhenius model. So a base is BOH, and it gets dissociated into B+ ions and OH- ions. And you have a couple examples. You have lithium hydroxide and potassium hydroxide being dissociated into lithium and OH ions, and the potassium hydroxide being dissociated into K+ ions and the hydroxide ion. Let's look at the next model, which is the Bronsted-Lowry model. This one is the most prominent one, and under this model, an acid is a proton donator and a base is a proton acceptor. Under the Bronsted-Lowry model, you have the same form of an acid, where you have HA dissociating into H+ and A- ions. But under the Bronsted-Lowry model, you have a bit more vocabulary. So first of all, we have our acid, which is HA. It's being reacted with water, which acts as a base in this case, and it produces that hydronium ion and the A- ion. The hydronium ion is going to be the conjugate acid, and the A- ion is the conjugate base. We'll define conjugate acids and conjugate bases in a little bit, but let's just first look at the general form of a base. A base is the same thing. You have B reacting with water to produce BH+ and OH-. In this case, B is the base and the water is the acid. The BH is the conjugate acid and the OH- is the conjugate base. So what are these conjugate acids? What are these conjugate bases? Well, a conjugate acid is the substance that forms after the proton is gained. So conjugate acids contain one more H+ ion than the base. So if you look at the acid, the base here is the water. So if you add one more H+ ion to the water, you have H3O. So that is your conjugate acid. In the case of the base, your base here is the B, If you add one more H plus ion to it, you have BH. So BH plus is your conjugate acid. And you can probably predict what the conjugate base is. The conjugate base is the substance that forms when a proton is lost. So conjugate bases contain one less H plus ion than the acid. So in the case of the acid here, your acid is HA. If you get rid of one H plus ion, then you're left with A minus. So A minus is your conjugate base. And in the base here, the acid is the water. If you get rid of one H plus ion, you're left with OH minus. You might notice that in the case of an acid, water acts as a base, and in the case of bases, water acts as an acid. So water can act as both an acid and a base. And compounds that can do that are called amphoteric. And this is one of the special properties of water. Okay, let's take a look at the last model, which is the Lewis model. In the Lewis model, bases are electron pair donators and acids are electron pair acceptors. So in this reaction here, you have H plus acting as a Lewis acid and the ammonia acting as a Lewis base to form NH4. The Lewis model is sometimes helpful because it explains properties of certain compounds that don't really function as as Bronsted-Lowry acids or bases. So the Lewis model is sometimes helpful in those edge case reactions. All right, let's take a look at the strength of acids and bases. So the strength of an acid or a base is going to depend on how much it dissociates. And to see what I mean, let's take a look at a strong acid. So an example of a strong acid is hydrochloric acid. So if I give you a solution of hydrochloric acid, you might expect on a molecular level for it to look like this. You have the HCl molecules all around. But this is actually not how it looks. Instead, it looks more like this. You have the H plus ions and the chloride ions separated. They're not together. And the reason for this is because hydrochloric acid is a strong acid. Then that means that its degree of dissociation is really high. Most of the molecules are going to be dissociated. They're going to be in their ion form instead of together as a molecule. So if you were to write the reaction of this, you would have hydrochloric acid being dissociated into H plus ions and chloride ions. You still have that equilibrium there because you have a tiny bit of that reverse reaction happening. Sometimes you're going to have the H plus ions and the chloride ions coming together to form that HCl molecule. But compared to the forward reaction, the reverse reaction is really unlikely. So since the forward reaction happens a lot more, we say that the equilibrium lies far to the right. You have a lot more products than you do reactants. And since it lies so far to the right, we can just get rid of that equilibrium symbol and just write the forward reaction. So hydrochloric acid dissociates almost completely into H plus ions and chloride ions. And if you look at the stoichiometry of that, you'll realize that the concentration of hydrochloric acid is going to be the same as the concentration of H plus ions. That little bit will be helpful a bit later on, but just looking at the stoichiometry for that, every mole of hydrochloric acid that you have is going to get dissociated. So 1 mole of hydrochloric acid is going to mean 1 mole of H plus ions. If you looked at a weak base, you would have a lot less dissociation. You would have 1 to 10% dissociation as compared to almost 100% as you do in hydrochloric acid, which is a strong acid. Let's take a look at base. A base is very similar. You have NaOH here. NaOH is a really strong base. And again, you might expect it to look something like this, where the molecules are kind of together. But that's not really how it looks like. Instead, they're all kind of dissociated. So if you were to write the general equation here, it would be NaOH is in equilibrium with Na plus and OH minus ions. But again, since you have so much of that NaOH being dissociated, we say that the equilibrium lies really far to the right because you have a lot more products than you do reactants. And since it lies so far to the right, we can just put a forward reaction instead of having that equilibrium. And the same as the hydrochloric acid, the concentration of the NaOH is going to equal the concentration of the OH minus ions. And again, that's because every mole of NaOH that you have, that's going to dissociate into Na plus ions and OH minus ions. So the concentrations end up being the same. So as we saw with strong acids and weak acids, a weak base is just going to have a lot less dissociation. It's going to have 1 to 10% dissociation as compared to like 100% like you do in a strong base. If you look at examples of acids, some of your strong acids are hydrochloric acid, hydrobromic, hydroiodic, nitric, etc. Weak acids, you have acetic acid, formic acid, sulfurous acid. These might be worth memorizing because they do come up a lot. If you don't want to memorize them and kind of just go through chemistry and by the end you kind of have this list in your head already, then that's totally cool. And let's look at some bases. So some strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide. Weak bases are going to be ammonia, methylamine, ethylamine, etc. Of course, you can't talk about acids and bases without talking about pH. So pH is just a convenient way to represent solution acidity. And pH actually has a formula. It's the negative log of the concentration of H+. So on the lower end of the pH scale, if you have something with a pH of 1 or 2, that's going to be highly acidic. And if it's on the upper scale, if it's like 13 or 14, that's going to be really basic. And again, pH has a formula. It's the negative log of H+. So lower numbers is very acidic, higher numbers is very basic. Now we also have another scale, and that scale is known as the pOH. So instead of pH being a convenient way to represent solution acidity, pOH is a convenient way to represent, I guess, how basic a solution is. And it has a really similar formula. It's pOH equals the negative log of OH ions, of the concentration of OH ions. And the number-wise, it's flipped. So instead of 1 and 2 being, very acidic, 1 and 2 on the pH scale is going to represent very basic. And higher numbers like 13 or 14 are going to represent very acidic solutions. Now, you might hear that pH and pOH go from 0 to 14. You can't have negative pHs, you can't have pHs over 14. But that's actually wrong. pH can be negative, pH can be over 14. So where does this 14 value come from? Well, at 25 degrees Celsius, your pH value and your pOH value must equal 14. And so that's where this number 14 comes from, but remember that pH can be negative and pH can go over 14. Alright, that's all I have for acids, bases, and the pH scale. If you have any questions, feel free to leave a comment. Other than that, that's all I have. I hope to see you later, and thank you for watching.